There is some incorrectness in generally accepted rationale for calculus.
Stop this bullshit. If calculus was wrong, how could modern science and technology grow out?
Those achievements are due to method for calculus rather than rationale for calculus. Rationale for calculus is a system to explain why the methods work. Method and rationale are two different things. Method for calculus is right, but rationale for calculus has problems.
I don't believe it. It has been 200 years since the publication of Karcher's analytical course.
What makes things right or wrong has no matter with when and who created it.
Why has no one pointed out the mistakes in calculus over the years?
Firstly, professional mathematical language constructs a barrier in modern mathematics. If people cannot master the professional mathematical language, they won't have the right to speak in mathematics. Secondly, in order to cover up the mistakes in the generally accepted rationale of calculus, some other mistakes are made. For example, an old wives' tale for the infinite set. One-to-one correspondence can be established between the subset and the whole set, is regarded as the truth. Thirdly, in order to eliminate the repulsion to the fallacies which can't be tolerated even by the intuition, the statement that the geometric intuition is unreliable is propagated. If you have any question about the mistakes of calculus, you can read the article, A Brief Discussion on Incorrectness of Generally Accepted Rationale for Calculus.
All these problems mentioned in this paper are about classical calculus, which had long been solved in the theory of functions of real variables and the modern analysis.
Is classical calculus that you are talking about still widely taught? Regardless of this, does the theory of functions of real variables really stand? We can have a good discussion. In order to enable more people to understand it, we discuss it in the vernacular mathematical language rather than professional mathematical language. In the last series of videos, we introduced 30's article, A Brief Discussion on Mistakes in Current Principles of Calculus. One may say, all these problems mentioned in this paper have been solved in the theory of functions of real variables and modern analysis. However, it's not true. Furthermore, the theory of functions of real variables, the fundamental content of which has become the prevalent basis of all the branches of the analytical mathematics, is untenable. In this series of videos, we will introduce 30's article, A Brief Discussion on Functions of Real Variables, as the perfection of principles of calculus. We will talk about in 5 aspects. The current theory of real numbers cannot justify itself. It's impossible to establish the one-to-one correspondence between the subset and the universal set. The premise of the demonstration of Cantor's theorem is untenable. The current real number system has no measure. Explanation of Liouville's inequality in the theory of functions of real variables is incorrect. Once one of them stands, it means that the theory of functions of real variables does have problems. The current theory of real numbers cannot justify itself. Now, let's talk about the first question. The modern mainstream mathematicians claim that the real number theory is rigorous and complete because it's based on scientific limit theory. The scientificity of the limit theory is indubitable because it's based on the rigorous and complete real number theory. Taken alone, these two sentences are unassailable, but put together they contradict each other. We will elaborate below. N is a sequence, and O is a real number. If a n can be arbitrarily close to r as n increases, we say that A is a limit of the sequence and only when E exists can we say that the limit of n is A. However, when defining real numbers, Bolzano and Weierstrass, as well as Merey, Heine and Cantor had hold the same idea. They all defined the real number system on the basis of the limit theory. Cantor, for example, defined a real number as equivalent to a fundamental sequence. Obviously, a sequence of numbers is different with a real number. Take the square root of 2 and the sequence 1, 1.4, 1.41, 1.414 as an example. The square root of 2 is static while the sequence 1, 1.4, 1.41, 1.414 is dynamic. But their relationship is in the sequence 1, 1, 4, 1.41, 1.414 keeps getting closer and closer to the square root of 2. However, due to the defects of the current number point model, number after number can be inserted between any two numbers. That is to say, no matter how close a number in this sequence is to the square root of 2, there are always infinite numbers between it and the square root of 2. Therefore, the dynamic approximation process is infinite, and it will never reach the square root of 2 itself. It is easy to see that the square root of 2 is the limit of the sequence 1, 1.4, 1.41, 1.414, rather than the sequence itself, or the equivalence class represented by this sequence. As we can see, in order to define real number system by equivalent fundamental sequences, the limits of those fundamental sequences must be pre-existing. To sum up, it is impossible to talk about limit without the existence of real numbers, and it is impossible to define real numbers without the existence of limit, which is the contradiction that current real number theory and the limit theory cannot overcome. Someone may say that Dedekind didn't use the limit theory to construct real numbers. However, his method is incapable of constructing the whole real number system. Dedekind said, whenever, then, we have to do with a cut which is not produced by rational numbers, we create a new, an irrational number alpha, which we regard as completely defined by this cut. The hypocrisy of the so-called Dedekind cuts lies in that this method can only construct real numbers of which the characteristics have already been known. In fact, we know little about the numbers except the algebraic ones. For example, we don't know how many categories the transcendental numbers can be divided into and what characteristics each category has. Therefore, the Dedekind cuts method is infeasible for numbers of which the characteristics are unknown. It is groundless to construct real numbers in this way. It is time to end this video here, and we'll talk about other mistakes of the theory of functions of real variables in the subsequent videos. It's impossible to establish the one-to-one correspondence between the subset and the universal set. Set that A, B, C, D and E are infinite sets. A equals B plus C plus D and C equals E. In this way, E is a proper subset of A. As another proper subset of A, C can have the one-to-one correspondence with E, which is guaranteed by the axiom. Thus E has no redundant elements, which can correspond to elements in B or D. This simple proof is applicable to both infinite sets and finite sets. How could it be different if the elements in A and E are infinite? Let's see how modern mainstream mathematicians argue. They assume that E can have such correspondence with B plus C plus D, in that both E and B plus C plus D are infinite, and neglect the difference in the increasing speed of n. This is not a proper practice, and it is very puerile that C and E are synchronously infinite, and once the one-to-one correspondence is established between these two sets, which can correspond to elements in B or D, anyone who gives the one-to-one correspondence between E and B plus C plus D has to demonstrate why this correspondence can exist. Someone may say, this correspondence can be demonstrated by enumeration. However, this enumeration can't end because these two sets are infinite ones. Some others may say, it's enough to complete the demonstration by giving a certain method of the enumeration. Unfortunately, this argument is untenable because any method of enumeration that neglects the difference in the increasing speed of two infinite sets, which is reflected in the relation of these two sets, is pure nonsense. When we say that E is the proper subset of A, the relation of E and A is obvious. This relation shouldn't be neglected. For instance, we will analyze the statement that the set of natural numbers can have the one-to-one correspondence with the set of odd integers, which is the proper subset of the former one. The former set is 1, 2, 3, etc., and the latter set is 1, 3, 5, etc. Even when n equals infinite, the n in these two sets are synchronous. Thus the former set is twice as large as the latter one. Certainly, someone may say, this logic is only applicable to finite sets. However, have the mathematicians who claim that the infinite sets have different properties given any convincing demonstration? These mathematicians acknowledge that the one-to-one correspondence can't be established between the set of all natural numbers and the set of all the real numbers. But these two sets are just infinite sets. Admittedly, one-to-one correspondence can be established between any bounded interval of real numbers and a certain set of natural numbers, and this correspondence is the usual count, which is opposite to Cantor's demonstration for his theorem in 1890. 06. Because these two infinite sets has no relations. Someone may say, no. The set of natural numbers is the proper subset of the set of real numbers. For this refutation, we want to say that the set of all the natural numbers is the proper subset of the set of all the real numbers, but not subset of the bounded subinterval of the set of real numbers. The premise of the demonstration of Cantor's theorem is untenable. Wow! Cantor proved Cantor's theorem in 1874. It tells us that all real numbers, or real number intervals, are uncountable. This is a crucial step in the establishment of infinite set theory. Cantor's theorem has been opposed by many people since its publication. And until today, the opposition has not disappeared. In fact, the proof of Cantor's theorem is wrong. How could this be wrong? Cantor also published other proofs later. Cantor's proof process concealed premises that could not be stated clearly. If the premise of proof is wrong, what is there to prove? The basic ideas of Cantor's theorem can be found in scattered locations in his specious paper, on a property of the totality of all real algebraic numbers, which was published in Journal in 1874. The demonstration that Cantor felt very convincing was published in 1890. The key points of the demonstration are provided below. Set that 0, 1 is a countable set. Then there exists a sequence, i.e., A1, A2, A3, An, which is composed of all the real numbers in this interval. Each real number can be expressed by a decimal, and set that the rational number can be expressed as an infinite decimal, then we have this. Next, we construct B equals this, set that if pkk equals 1, then bk equals 9, if pkk not equal 1, then bk equals 1. Hence, B is a real number, in the interval 0, 1, but it doesn't equal any real number in the above sequence, which contradicts the hypothesis. Therefore, 0, 1 is uncountable. Similarly, any interval of real numbers is uncountable. The premise of the above demonstration is false. The real numbers can't be written as infinite non-repeating decimals because the proposition that we want to demonstrate is a pure mathematical proposition, but not an applied mathematical one. As is known to all, the rational numbers aren't infinite non-repeating decimals. However, it should be noticed that the irrational numbers are only themselves and they aren't infinite non-repeating decimals, either. The infinite decimals are dynamic numbers and indefinite numbers. But the irrational numbers are static numbers and definite numbers. From the perspective of the sequence, the irrational number is the limit of the infinite non-repeating decimal, which can be regarded as a sequence of decimals. but not the sequence or the dynamic process itself. Cantor's error is that he equated the irrational number with the dynamic process of the infinite non-repeating decimal, i.e. the sequence of decimals. That is to say, Cantor confused the limit of the sequence with the dynamic extension of the sequence. There is another method of demonstrating Cantor's theorem, which is intuitive. Of course, this method can only give the proof by contradiction. 2. Set that all the points in 0, 1 can be sequenced as 1. Let us enclose the point with coordinate a1 in an interval of length 1/10, the point with coordinate a2 in an interval of length 100th, and so on. If all points between 0 and 1 were included in the sequence 1, the unit interval would be entirely covered by an infinite sequence of possibly overlapping subintervals of lengths 1/10, 100th. The fact that some of these extend beyond the unit interval does not influence our proof. The sum of these lengths is given by this geometric series. Thus the assumption that the sequence 1 contains all real numbers from 0 to 1 leads to the possibility of covering the whole of an interval of length 1 by a set of intervals of total length 1/9, which is intuitively absurd. This demonstration is applicable to any other unit intervals. Therefore, Cantor and his supporters held the opinion that Cantor's theorem was tenable. However, there is also a fatal error in the premise of this proof by contradiction. It is considered with no reliable arguments that the mathematical holders of the measure are points or numbers. In fact, on the basis of the current number point model, these holders can only be the blanks between points in the continuous interval. We will elaborate this proposition when discussing the measure in the next section. If we consider the blank between points to be the mathematical holder of the measure, then we have delta I equals 1 minus 0 divide n. And formula 2. Only in this way can we comprehend the measure reasonably. The false conclusion drawn from the absurd demonstration that imposes the length on the points or numbers, which aren't the mathematical holders of the measure, is definitely untenable. Furthermore, the theory of functions of real variables changes the right things into wrong things, while demonstrating that the mistake in the classic rationale, calculus, doesn't exist through making another mistake, which contradicts the original purpose of this theory, that is to support and perfect the classic rationale for calculus. In the classical rationale, the integral is defined by formula 3 or 4. However, in the theory of functions of real variables, and can only be countably infinite while there are uncountably infinitely many numbers in the interval a, b, and every number in this interval can be represented by x. According to Cantor's theorem, n can't enumerate all the numbers in a, b. Therefore, the equality 5 isn't reasonable according to the theory of functions of real variables. As a matter of fact, although Cantor's theorem is provable by contradiction, the indirect method, direct constructive proofs, could not possibly be given even in principle. True mathematicians like Poincaré, Brouwer, Weil didn't approbate the unserious views from Cantor to Hilbert. The current real number system has no measure. The length of the interval a, b, is b minus a, which is very consistent with people's intuition. Extending the interval length to the measure of the set, Lebesgue established the measure theory. This is exactly what Lebesgue said: I wish first of all to attach to sets numbers that will be the analogues of their lengths. Here, Lebesgue regards the interval a, b as a set consisting of all rational and irrational numbers between a and b. We naturally ask, who is responsible for the length of the interval a, b? In other words, who is the mathematical undertaker of the measurement? There is a contradiction here. How does a number without a measure, with a measure of 0, constitute an interval with a measure? In order to conceal this contradiction, Labes have to resort to the wrong infinite set theory, and describe the irrational number, or transcendental number, as the mathematical undertaker of measurement. Why are irrational numbers, or transcendental numbers, the mathematics undertaker of measurement? Answering this question directly will still fall into the aforementioned contradiction. However, with the help of infinite set theory, the method of elimination can be used to complete the proof process. The following is the main logic of the demonstration of this theory. The intervals and the line segments corresponding to the intervals have positive measure, and the measure of any algebraic number, and its corresponding point is 0. However, the interval, and its corresponding line segment, is composed of the algebraic numbers, and their corresponding points, and the transcendental numbers, and their corresponding points. Therefore, the transcendental numbers and their corresponding points are the mathematical holders of the measure. What is wrong with Lebesgue and others? In fact, the interval and its corresponding line segment are not composed by two kinds of things but composed by three kinds of things: the algebraic numbers, the transcendental numbers, and the blanks between numbers. It was ridiculous to arbitrarily assert that the transcendental numbers, and their corresponding points, were the mathematical holders of the measure when merely the algebraic numbers, and their corresponding points, were excluded because those mathematicians didn't know the existence of the blanks, which are as many as the real numbers. As a matter of fact, the real numbers have never filled up the number axis because the numbers and points in current theory have no size, whereas the number axis does. Blanks can always be found on the number axis no matter how many points without size there are. Any demonstration based on such assumption that points without size can fill up the entire axis is untenable. Numbers can't have measure while quantities can. The quantity is the difference of two numbers. When considering analytic geometry properties, there is no difference between points corresponding to algebraic numbers and points corresponding to transcendental numbers. Therefore, if the algebraic numbers are not the mathematical holders of the measure, then the transcendental numbers can't be the mathematical holders of the measure, either. If we examine the measure theory from another perspective, we can also find this theory untenable. The measure of one transcendental point, or number, is 0, and the measure of countably infinitely many transcendental points, or numbers, is 0, too. However, the measure of uncountably infinitely many transcendental points, or numbers, is a concrete number which isn't 0. Why is it so? Without any explanation, how can we accept this kind of logic, besides forcibly accepting it? Apart from the set of all real numbers, and the unbounded sets of real numbers, no number sets have uncountably infinitely many numbers. The set of the entire natural numbers is the proper subset of the set of the entire real numbers. Thus the one-to-one correspondence shouldn't be allowed be established between these two sets. However, the set of entire natural numbers isn't the proper subset of the bounded subinterval of the set of entire real numbers. Therefore, there aren't any correlations between these two sets, and the one-to-one correspondence can be established between the set of natural numbers and any bounded interval of real numbers. This is why any bounded interval of real numbers is countable. Explanation of Liouville's inequality in the theory of functions of real variables is incorrect. Liouville's inequality, i.e. Formula 1, is interpreted that there must be a gap of at least 1 of a star times q to the nth power between the irrational x0 and any rational p of q. And a conclusion follows that the algebraic numbers are spotted over the plane like stars against a black sky. The dense blackness is the firmament of the transcendentals. Therefore, The so-called theory of transcendental numbers is seen as the base for Lebesgue's measure theory. The above explanation of Liouville's inequality is incorrect. On the contrary, when q tends to infinity, a star times q to the nth power tends to 0. That is to say, as q increases infinitely, the rational p of q can approach the irrational, or the transcendental, x0 infinitely. In fact, the irrational p of q can approach x0 infinitely regardless of whether x0 is an irrational number, or a rational one, because a star times q to the nth power tends to 0. Of course, the transcendental numbers aren't mentioned in the Liouville's inequality. Can the rational numbers q plus 1 of q to the qth power approximate e? If this approximation is obstructed by a constant quantity, even though this quantity may be tiny, it can't be said that this irrational number is approximated by rational numbers properly. On the contrary, as the formula 2 and 3, where x can be any positive number, i.e., when x tends to infinity, there exists the inequality 4 where epsilon is an arbitrarily small positive number, so it can approximate e perfectly. Actually, even Liouville himself didn't give any rational explanations of Liouville's inequality. In 1844, Liouville pointed out that algebraic numbers can't be approximated by rational numbers perfectly. By the function 4 and setting that px and qx equal this, Hermite got the equality 5 where rx equals this. Finally, he got the inequality 6, or this, where q is greater than or equal to c and c is a constant determined by epsilon. If we compare 4 with Dirichlet's inequality, where theta is an arbitrary real number, q is an arbitrarily given real number, which is larger than 1, and both p and q are integers, we will find that the explanation of Liouville's inequality given by the current mathematical world is incorrect, because theta in Dirichlet's inequality can be x0. In Liouville's inequality, the crucial point is that q is set in order to approximate a certain real number, that is to say, q tends to infinity. This series of videos is coming to an end. Finally, let's make a summary. The analytical mathematics, especially the modern analysis, has never been what is comprehended by mathematicians who know little about the mathematical history, and has never been what is written in current mathematical textbooks. Mathematicians represented by Poisson had never been in favor of Rationale, the calculus established by mathematicians represented by Cauchy. Moreover, mathematicians represented by Poincaré and F. Klein had never been in favor of the theory of functions of real variables. People seem to have forgotten that Poincaré, Klein and Hilbert were three huge figures, standing on the boundary between mathematics in 19th century and mathematics in 20th century. Unbelievably, the so-called theory, which was opposed by two of the three huge figures, became the mainstream with the support of Hilbert. There must be some reasons outside the mathematics. All in all, some of the demonstrations shown above may not be undefective. However, if one of these demonstrations is tenable, the theory of functions of real variables, which is regarded as a perfection of current rationale, the calculus is bound to be untenable. Speaking of which, friend, you must understand, all the information is listed here, and can be accessed by interested readers.